again, our topic is on chip network traffic pattern clustering in Jiayi. This is Jinxi, and that's PP. So let's go into the outline, the background. So here is an 8x8 mesh on chip network. And we can see there are different patterns as time goes by. So here we need to, I'll give you some background on the data we're collecting for and the features that we're using. So the original feature that we're using is source destination flow rate. So in the network, the flow, we call the flow as a source destination pair, and the flow rate is number of messages sending from the source to destination within a given time period. And the link utilization rate is for each link the number of messages traversing the link within the time period. So here is the motivation. Because the advanced semiconductors technology and only provide a limited performance improvement. So that requires deeper understanding on the application demands and architectural innovations. Our goal of this project is we're trying to characterize the on-chip network traffic behaviors using clustering techniques to explore the potentials for system performance improvement and power efficiency. Here's one existing related work on the on-chip network traffic clustering. However, they have several limitations. They only take the source destination flow rates, and there's no any information about what path that message are going to take. So due to that limitation, there are limited opportunities that we can use for adaptive routing and congestion control design. And the global control they take in the paper is not a scalable solution as the network scales, and it faces the 1-point failure risk. So objectives of this work is, in order to overcome the limitations, we include the link utilization rates as a feature vector to explore optimization opportunities for adaptive routing design and congestion control. And we'll also propose the region-based instead of the global approach to cluster regional traffic patterns to approximate the global state, which is a more scalable and reliable solution. And we then will analyze the traffic patterns and interpret the feature vectors. So let's go to how we collect the data. So we run parallel applications on the full system simulator to get the network traces, and then we feed the network traces into the network simulator. And during the network simulation, we profile the source destination flow rate and the link utilization rate across the program execution time. And we sample those rates given a sample period and generate the data examples. And in order to use the regional features, we partition the network into 4 regions. And we have 2 regional features. One is the region core features vector, another is the region flow vector. So in the region core feature vector, we add all the flow rates from the cores inside the region to all other cores outside the region. The difference between the region flow and the region core feature vector is that we virtualize all the outside cores in the outside regions as a supernode. And then first of all, we get all the flow rates and link utilization rates, and we do feature reduction to get the average or the source or the destination and so on. And we do the same thing for the regional feature.
So the clustering tool we use is Python clustering library. We test on the k-mean and hierarchical algorithm, which both of them provide us a similar result. So all the results down for the following slides is from the hierarchical algorithm. To justify our result, again our goal is to put the similar behavior into the same cluster. So an intra-class variation will be computed for all the clusters, and also this applied to the problem. we know the same class should have similar package latency delay and the similar power consumption. So this is the intra-class variation for the global data set. All the intra-class variation are very small. It's like 0.408. That's the biggest one. And when the number of cluster increase, the variance decrease. And I want to mention the link feature we add into the feature set is also relatively smaller compared to the others. So we also compare the regional set with the global set. Although those regional set has a little bit higher variance, but it's still relatively very small. We also compare the second region. So as to summarize, we have all the global and the two region data can have a high quality clustering result according to the intra-class variation. And our link utilization rate at the future is very good. So let's talk about the latency and the power. So this is the coefficient of variance for the power consumption for the global data, and this is latency for the global data. I want to mention the flow and the package latency delay is directly related to the traffic load on the on-chip network. So flow and link rate will provide us the smallest COV for the latency. So in order to have a deep study about the data we have, we visualize the class transaction behavior and the latency power behavior over a given certain time period on one benchmark we select. So all the x-axis is the time cycle, which each point represents 1 million cycles. So, and for the first and second graph, the y-axis is the class ID. So for example, for the time 50, we have a y reading 4, which means on time 50, we have a class, a behavior belong to the class 4. And look at this graph, we have class 4 and class 3. So compared to the region class transaction behavior, we can see when the regional switch from a class 3 to the class 16, we also have a class 3 switch to class 4. So the behavior for the regional class transaction is very similar to the global class transaction, which approve our regional feature pattern can have the approximate result compared to the global. So the third one, we have the latency value over the time as the blue line, and the power value over the time as the red line. We compare back to the first graph. So when it appears as class 4 here, this long line, the power consumption is really, really high. And when the class 4 switched to the class 3, the latency suddenly increased. So we wonder why it's happening. So for a better understanding, we visualize the flow injection rate central into a grayscale matrix. And also we visualize the link utilization rate as a mesh diagram. Let me explain a little bit about this. So the x-axis is source, and the y-axis is the destiny node. So the darker the square is, means there more communication happen from the source to the destiny on the targeted node. So let's look at the class 3's graph. For the class 3, the node 3 here is very dark. It means there are more, node 3 is receiving more data, is receiving more package from all the other cores. So all the package is trying to go into the 3. So it's also mapped here. So all the link surrounding the number 3 is wider than the other links. So which means 3 can create a very high latency because everyone is trying to get into there. So for the class 4, we have communication distributed evenly over the whole network. So which every link here is wider, and everyone is trying to communicate with each other. So we have higher power consumption for class 4. but because we distribute evenly, so the latency is lower compared to the class 3. So we actually animate different class behavior into this. So you can see for the 32 cluster and the 128, they have some similar. So different class have different behavior. So in conclusion, our link utilization rate as a feature is very good to provide us a high quality clustering result. Also, we proved that the region-based clustering will give us an approximate result compared to the global, and which make our optimization more scalable and reliable. So our future work is apply what we learned here into the optimization process. We will go to explore the code-to-code communication pattern to design a reconfigurable network topology to provide a highway for the high-frequency communication code pairs. Also, we were going to develop a dynamic routing algorithm for the congestion control by using the link utilization knowledge we learned. Any questions?
So you're measuring the link utilization. Is that a cheaper measurement than other ways of measuring congestion or activity?
You mean cheaper way? Because especially in large-scale network, if you want to measure the congestions, you need to get if you only measure the local congestions, you can just measure your links that connected to this node. But you can't. The local information is very suboptimal. So even though you send out, maybe there's a far end congestion point there that you will face more blocking. So but however, if you take the global way to get all the link utilization from across the network, because it incurs very high overhead to get all the results. So we propose to use regional based, we just get a small area to get a sense that to approximate how the congestion is in the total network.
Okay, we are out of time, so thank you guys.